Right, question about waves. Part A. Explain what happens to the wavelength of light when it passes from air into glass. 2 marks. Okay, what happens to the wavelength? So, say what you know. Okay? When light passes from air into glass, the velocity decreases. Okay? The velocity. Okay? You also need to know that the frequency remains the same. Okay, you've got to remember that. So commit that to memory right now. When light goes from air into glass, the velocity decreases, but the frequency is the same. Right? Now, write down the wave equation. V is F lambda. And this question is asking what happens to the wavelength, that's lambda, of the light. Okay? So V is F lambda, therefore rearrange. Lambda is V over F. Okay? So, therefore, if the velocity decreases, so the thing on top's getting smaller, the frequency, the thing on the bottom is the same, therefore the wavelength, lambda, gets smaller or decreases. Okay? Definitely got the 2 marks with that explanation. So, remember, when light goes from air into glass, the velocity decreases, but the frequency remains the same. Just remember those two. You have to know the wave equation. Remember that as well. V is F lambda. Velocity is frequency times wavelength. And therefore, the wavelength must decrease. Okay, part B. An agonizing 6 marker. Okay, discuss the path of the wavefront AB as it enters and leaves the glass block. Here's our glass block, here's the wavefront AB. Okay, first thing I do in an exam is complete the diagram. Show what you know, okay? So, exam technique. Say the obvious, say what you know, and put it all in a logical order, right? That's how you do exam questions. So, we're going to show what we know here. We know how refraction works. So we're going to draw this being refracted and leaving again on this side. First thing when doing refraction is draw in the normal, okay? Just a faint line like that, perpendicular to the glass block, okay? Second, draw a few dots to show the straight through direction where the, the light would go if the glass block weren't there, it would just keep going. And now we're going to draw the light beam on the inside. Let's do this one first. It's going from air to glass. When it goes from air to glass, it moves towards the normal. Okay, so it would be going in that direction. There's the normal, so it moves towards the normal. It's going to move to there. So it's going to be down there somewhere. Okay? Same thing here, move towards the normal and get these 2 lines parallel to each other. Okay, I didn't draw that brilliantly. They're not quite parallel, but they're meant to be. Right. Same thing here. Step 1, draw in the normal. Okay, you can put a little right angle there if you want to show that's the normal. Okay, step 2, draw in the straight through direction. And step 3, when it's going from glass to air, it moves away from the normal as it speeds up. So there's the straight through, it moves, there's the normal, there's the straight through moves away from the normal, so it's going to be over here somewhere. And the final thing for icing on the cake if these two sides of the glass block are parallel, and they are in this question, then get the two beams leaving the glass block parallel to the original two going in, okay? So this line I'm about to draw should be parallel to this one. So it's going to be something like that. Is that parallel? And the same this one here. Rubbish. It's not parallel. But I'm not going to redo it. It's meant to be, okay? These two are meant to be parallel to those two because it's a these two sides of the glass block are parallel. It's annoying. Anyway, let's just get on with it. As long as you know that these two are meant to be parallel to these two. Right. Okay, so we've demonstrated a bit of knowledge already. Okay, so the wavefront AB is going to be something like that, inside, and like this on the outside. Okay. So, we've drawn a bit on the diagram in the question sheet, in the exam, and we've shown already that we know how refraction works, even without writing anything. So we've already got the examiner on side. Right, now, looking at the question, it says, discuss the path of the wavefront AB. It wants us to focus on the wavefront. It's not asking us to describe like a single beam of light, for example. It's talking about the actual wavefront. So answer the question, focus on that. Discuss the path of the wavefront AB's enters and leaves the glass block. Look, what this question's getting at is when it talks, the question asks about wavefront and how it moves through a glass block. It's trying to get you to describe how refraction works. Okay, so that's what we're going to do. So, first thing, as this wavefront approaches, what's going to happen? Point A is going to reach the glass block first. Okay, so we'll say that A reaches first. You should write this out in full sentences. I'm going to do it shorthand for time. A reaches the block first. Okay? Next. Point A enters the block and slows down. Okay? Enters the block and slows down. Okay? This question it's part B. It's not really connected to part A, what we've done here. So say what you know again here. It slows down because light is slower in glass than air. Okay? Good. Right, next. So at this point, point A, we're about here. A has entered, I'll draw it on. Okay, A has entered the block, but B is still outside. Okay, so say that. So B is still in air and moving faster. Okay? Right. And it's probably a good idea to draw that on. See how I've got the line from A to the boundary is parallel to this wavefront, and this bit here is parallel to that wavefront. Okay, so all this causes, how did I put it? Yeah, this causes the direction of the wavefront to change. inside the block. Okay? And this is what refraction is. This is called refraction. Good. Okay. Yeah, you should mention the obvious again. Just say everything you can think of that's relevant, okay? You'll probably get a mark for it. The change of direction is towards the normal. Okay? See, it was going to go through like that, but it moved towards the normal. Okay, what else? Right. So that's covered this bit here to this bit. So now we've got to cover leaving. So point A reaches the air, the boundary first. So point A reaches the air first. Point A exits first is probably a better way of saying it. As it does so, it speeds up. Speeds up. The whole process is reversed. The wavefront moves away from the normal. From the normal. Okay? And if you want, you can say, this is just probably not necessary, but if you want, no harm in saying it. If these two sides of the glass block are parallel, then the wave exiting the glass block will be parallel to the wave entering the glass block. Or we're talking about the wavefront here, so if you want, you can say the wavefront will head in the same direction as it was when it was no, it's not technically the same direction, is it? Because it's being shifted over here. The wavefront will move parallel to the wavefront when it entered the glass, before it entered the glass block. Okay. Right. Good. Is that everything? Yes, it is. Right, let's move on to part C. Do that in a different colour, why not? Right, the Earth-Sun distance is 1.5 times 10 to the 11 meters, okay? And light takes 500 seconds to go from the Earth to the Sun. From the Earth to the Sun? Actually, technically it does, yes. The little light that does leave the Earth will reach the Sun in 500 seconds. To go from the Sun to the Earth, focus, Pearson. Sun to the Earth. Right, good. The wavelength of red light is 670 nanometers. And we have to calculate the frequency of this red light. Right. No problem. Right. So we're dealing with frequencies, wavelengths, write down the wave equation. V is F lambda. Okay? Always a good start. Next, it's asking us for the frequency. So it's rearranged for frequency. frequency, bring the lambda down here, is v over lambda. Right, so they've told us lambda, easy, don't have to do anything there, it's 670 nanometers. Velocity, that's what we have to calculate. They've given us the distance and the time, okay? Speed is distance over time, or velocity is distance over time. So, velocity is distance over time. Speed is distance over time, you knew that, right? So therefore, the frequency, combine these two, okay? Frequency is v, so we're subbing in this into here. So distance over time, frequency is velocity, that's that bit, divided by lambda. So lambda goes on the bottom, we can just stick it on the bottom like that. Okay? Does that make sense? Don't go doing d over t and then all over lambda, okay? It's just, if velocity is distance over time, and you have to divide that by lambda, dividing that by lambda just means putting lambda on the bottom, okay, next to the t. So it's t times lambda on the bottom. Okay, stick in the numbers. Frequency is distance, 1.5 times 10 to the 11. Get it in the right unit, it's already in the right unit, meters. Divided by time, 500 seconds. Need it in seconds? It's already in seconds, so it's 500. Good. Wavelength, 670 nanometers. 670. Now that's nanometers. We have to put it in meters. Nano is times 10 to the minus 9. Okay, there it is. So stick that in your calculator and you get frequency is 4.47761 something something something, who cares, times 10 to the 14. So therefore the frequency is, this is too much, let's do it to 4.5 is sensible. So that's 7, push that 4 up to a 5, 4.5 times 10 to the 14. Frequency, the unit is hertz. There we go. That was a nice little calculation to finish off with. Yeah.